Hello, my name is Jessica Lazarus, and I'm a PhD student at the Institute of Transportation Studies at UC Berkeley in the Department of Civil and Environmental Engineering. I'd like to start off by thanking Jesse Lee and the other organizers of today's workshop for the opportunity to present this research on multi-objective transportation system optimization using BISTRO, the Berkeley Integrated System for Transportation Optimization. BISTRO is an open source transportation planning decision support system that uses an agent-based simulation and optimization framework to develop adaptive strategies for the technological disruptions and growth that we are seeing in transportation today. I'll start off with some background on the state of practice of travel modeling and transportation planning and policy before diving into an overview of BISTRO and the optimization problem that it solves. Then I'll present the experience of beta testing BISTRO with a hackathon on the scenario called Faux. And finally, we'll discuss ongoing work that we are doing on congestion pricing optimization using BISTRO. The transportation landscape across the globe has changed rapidly in recent years. The advent of real-time traffic information and dynamic routing services have given way to the adoption of on-demand mobility services, such as bike sharing, car sharing, transportation network companies or TNCs like Lyft, Uber, and DiDi. And these services are highly dynamic and built upon the optimization of the distribution, relocation, and pricing of supply so as to maximize the level of service provided to their users at the moment that they open their phones ready to make a trip in the fastest or most convenient and comfortable way possible. In contrast, transportation planning and policymaking is traditionally carried out across much longer timelines, with a major focus given to the medium or long-term equilibria of the transportation system. In the US in particular, states and metropolitan planning organizations are responsible for forecasting and analyzing policy and infrastructure development scenarios at the regional level in order to evaluate their potential positive and negative externalities. These plans that are put forth incorporate transportation, housing, economic, and environmental strategies to meet the policy goals that are set forth by the state. The figures here and in the next couple of slides are examples from Plan Bay Area 2040, which is the long-range plan for the San Francisco Bay Area that was adopted by MTC, the Metropolitan Transportation Commission, and ABAG, Association of Bay Area Governments, in 2013. Plan Bay Area 2050 is actually currently under development and is expected to be adopted in the summer of 2021. So here we have a couple more examples from Plan Bay Area 2040 where you see some examples where discrete scenarios of transportation infrastructure expansion are modeled. And you can see here on the left, road pricing scenarios are shown versus on the right, regional transit system improvements are modeled and analyzed. The scenarios are typically evaluated using a set of metrics that reflect the impacts of these scenarios on system-wide performance in terms of congestion, pollution, and levels of service, among other metrics across the transportation system. Accessibility and equity are also commonly used, as well as metrics of economic vitality, which are typically included as well. Analogous processes are also carried out at the local level for other sorts of planning and policy decisions, such as congestion pricing, transit service planning, and city-level infrastructure investments. Here you can see two examples of scenario analyses of congestion pricing that were carried out in New York City and San Francisco in the left and right, respectively. The approach that is generally used for these system-level decisions is called travel modeling. While there are several different models that may be used, the objective is generally to represent all of the multiple interrelated dynamics of regional travel behavior as comprehensively as is appropriate for the questions and objectives under consideration. A schematic of the MTC's activity-based model called Travel Model 1 is shown on the right here to give you an idea of some of the more complex models and what they look like. Most recently, activity-based models have grown in popularity, and this is largely due to the fact that they can incorporate the linkages between multiple aspects of travel and are capable of producing individual level forecasts of travel behavior. As you can see in Travel Model 1, in the schematic on the right, Activity-based models synthesize a sample of individuals that are socio-demographically representative of the regional population. Each individual has their own daily activity plan that specifies a schedule and locations of activities that are also spatially and temporally representative of travel behavior in the region. These models can vary in the number and complexity of decisions that are simulated for each agent. And in addition, a key aspect of any one of these models is the transportation network model, which specifies the physical dynamics of the system. That includes the operations of transit and on-demand ride services, vehicle routing, and congestion effects throughout the network. As activity-based models have grown in popularity, so has the agent-based simulation as a tool by which to implement these multifaceted models. Agent-based simulation enables us to explicitly simulate the decisions and movements of individual travelers and vehicles, which are the agents in the transportation system. At the core of these simulations are representations of the road network, the transit network, land use, and infrastructure, all of which define the physical constraints of vehicle movements, including the real-time speeds on each link of the network as vehicles are routed along their assigned or chosen paths from one location to another. Individual travel decisions are simulated and carried out in response to the real-time conditions of the network, which determine the travel times and costs of the travel mode all of the travel modes available at the time of departure for a particular trip. In practice, travel demand modeling is typically used for policy scenario analysis using discrete policy inputs constrained by a priori analysis. These scenarios are modeled and evaluated according to multiple criteria, and decisions are made as objectively as possible. But the pursuit of multi-objective policy optimization is at this time limited. While certain operational aspects of the transportation system are increasingly optimized, under the public control, an example would be traffic control, or privately, vehicle automation and fleet management of services such as TNCs are being increasingly optimized. However, we have yet to build out the capability for truly dynamic and socially optimized policy design and implementation. At this time, the capability for high fidelity predictive analysis of the impacts of interventions in the transportation system or changes in policy are sparse and highly resource intensive. It's costly to develop a well-calibrated travel model, as well as to run and analyze a large set of potential scenarios. Thus, there are concentrated resources mostly at the MPO level, and there's discrepancies across MPOs in terms of their capabilities and ability to model more complex scenarios and do more scenarios. And even then, the calibration and validation of these models are limited by the scarcity of accessible data. Individualized or household level travel data is usually acquired on a cycle of about 5 to 10 years using travel diary surveys. Network level and even link level travel time and speed data is becoming more available. For example, companies such as Uber have released data on their Uber Movements and Uber Speeds platform, although this data is only available for select cities. It can be used for those cities to help calibrate these models and make them more accurate. The availability of other data sources also varies by geography. So nonetheless, simulation does serve the essential purpose of enabling researchers and practitioners to execute predictive analysis of interventions in the transportation system. And those could range from changes in the distribution of travel demand to changes in the supply, governed by vehicle access, operations, and pricing, or any number of other policy inputs. So now we'll turn our attention to BISTRO, which is the Berkeley Integrated System for Transportation Optimization. BISTRO is an open source framework for transportation policy decision support and optimization that was developed by researchers from UC Berkeley at the Institute of Transportation Studies in collaboration with Uber Technologies. BISTRO functions as an optimization superlayer to the agent-based simulation engine called BEAM, the Behavior, Energy, Autonomy, Mobility Framework, developed at the Lawrence Berkeley National Lab, also by ITS-affiliated researchers. BISTRO has a number of modules that you can see on the left that enable the optimization of multiple policy-related inputs that effectively alter the operation of a defined transportation system in a given scenario, and which is simulated through BEAM. The inputs can be constrained and validated according to a defined set of what we call business rules, which ensure that policies are optimized within a defined realm of realism. And BISTRO parses the raw beam outputs once a beam simulation has been run in order to evaluate a set of user-defined objective functions that can be used in optimization. And we have also developed a library of suggested optimization algorithms that can be deployed. And we use Docker containers to facilitate OS-agnostic, local, and remote execution of BISTRO. Some examples of the optimization inputs include pricing, which can alter public transit or on-demand ride fares, operational adjustments for public transit and on-demand ride services that can change the number or mix of vehicles in either fleet, as well as they can alter the schedules, and we can also alter on-demand vehicle availability through rebalancing algorithms. And finally, infrastructure investment is another policy input, which could include the location of vehicle charging stations or the quantity and location of parking facilities. So we have also developed a number of key performance indicators which serve as the objectives of an optimization, which comprise of system-wide indicators of congestion, social impact, operational performance, and environmental impact, some examples of which are listed here. These objectives can be either aggregated or disaggregated as needed, as desired by the user. And additional objectives can also be specified as a function of any of the outputs that are parsed from Beam. Those outputs include detailed data from every traveler decision and every vehicle movement throughout the simulation. So you can just imagine the possibilities of what kind of study could be set up using BISTRO. And finally, BISTRO stores the parsed data in a relational database that powers a visualization dashboard, which you can see in this video, that can be used to investigate different policies and can compare BISTRO runs side by side using visual analysis of key metrics. And those metrics are shown disaggregated across time of day, across the network, and across sociodemographics in the synthesized population. It's really quite useful. Now, I'll dive into the actual optimization problem that BISTRO solves, which will hopefully help to concretize what it is that we're optimizing. So the problem is broadly referred to as a simulation-based optimization problem. Here, I'll provide a brief overview, and then I'll go into some more specifics in the following slides. The key variables of interest include a decision vector or policy input, which we call D, the configuration inputs, which are fixed data, those are Z, and then the simulation outputs that result from running the simulation using a given configuration and policy. We note the constraints here is the function G, and you can see that we consider the objective functions, denoted as big F, to be stochastic, as there is a considerable amount of stochasticity in an agent-based simulation due to the stochastic nature of the behavioral models that are used, or perhaps other models if we're talking about a different simulation. In transportation in particular, the main source of stochasticity is indeed in the behavioral dynamics. So for that reason, we optimize the input based on the expected value of the objectives. So more specifically, in a simulation-based transportation system optimization, the first step is a scenario configuration, which involves specifying the transportation network, which includes the location of all nodes and links in the network, as well as the attributes that define the capacity of links and the speeds of vehicles in the network as a function of the volume of vehicles throughout. Next, mode-specific parameters are also part of the configuration, and these define the characteristics of each of the modes. Modes can include walking, driving, biking, public transit, and on-demand rides. So these parameters will specify fares, pricing, schedules, and other operational parameters. Next, the vehicle parameters define the type and number of vehicles operated by each agent or transportation service operator, such as public transit operator or an on-demand ride service operator. And finally, the population parameters define the individual characteristics of travelers, which include the size and location of households, travel plans of individuals, and sociodemographic attributes. Again, these are all fixed data in the simulation. So, as I said, one of the main sources of stochasticity in a transportation system is the behavioral dynamics of the mode choices. This variable that I'm showing here defines what mode is used by individual N for a trip from I to J at time T, given the configuration of the network. So in BEAM, mode choices are modeled as utility maximizing decisions, where the probability that a mode is chosen by a particular individual for a particular trip is equal to the probability that the utility of that trip using that mode is greater than the utility using any other mode. The utility is a linear function in this model of the attributes of a trip, which include travel times and costs, but they can also include other parameters such as the trip purpose or destination of the trip, as well as other parameters that you could include signifying comfort. For example, is it a pooled trip or not? How many passengers are in the trip? Things like this. Utility can also be a function of individual characteristics as well. So one of the models that can be used to compute this probability is the multinomial logistic regression, or logit, which is shown here in this ratio. And we'll keep that here for reference. The outcomes of the mode choices essentially determine the distribution of vehicle demand across the network. In BEAM, vehicles are routed on the fastest path available in the network, which is calculated dynamically as vehicle movements are simulated, producing travel time estimates per link on the network on a second per second basis. So then, of course, the resulting distribution of vehicles affects the trip characteristics as it affects the travel times. And those in turn will affect mode choices, which will affect the distribution, and so on and so on. In BEAM, a simulated period, such as 24 hours of travel, will go through multiple iterations in order to reach equilibrium. So as I have described previously, BISTRO enables the specification of policy inputs, which essentially alter the outcomes of trip characteristics, and parses the BEAM outputs into any number of specified system objectives. So you can imagine here that in addition to each of those key X variables being dependent on Z, that they're also dependent on D. So then BISTRO enables the optimization of those inputs based on the specified objectives. And I will give some examples of those optimization algorithms that we have developed for BISTRO in a moment. But the user is certainly free to develop their own approaches as they wish as well. So now we'll discuss the Uber Sioux Faux Hackathon, in which we beta tested BISTRO in the spring of 2019 as part of an internal hackathon among employees at Uber. We wanted to test the usability of BISTRO while posing a difficult challenge to folks in the AI and ML communities at Uber. The hackathon was posed as a competition to optimize 4 policy inputs for a fictional scenario with 9 different policy objectives. So for this purpose, we adopted an activity-based model of the city of Sioux Falls, South Dakota, which we call Sioux Faux for the purpose of this case study, as well as others that I'll discuss later. So we've essentially created a Sioux Faux benchmark scenario that can be used in BISTRO. The distribution of the population density, household income, and age are shown here. And we produced a sample of 15,000 agents, with each agent completing one activity during the simulated day, which is either a work or secondary activity. Secondary activities include groceries, errands, leisure activities, etc. And agents could choose between walking, driving, and transit, with free access options to transit, as well as on-demand rides. We adapted the Sioux Falls bus network as the sole public transit service in the city. So when we say public transit for the Sioux Faux scenario, we are referring to bus. And in the base case, which we refer to as the business as usual, or BAU, we have about 3/4 of agents choosing to drive. So in this competition, contestants were tasked with the challenge of reducing congestion with a number of operational and financial constraints that I'll discuss shortly. So contestants could alter any or all of the following inputs. And you do have some examples of contestant inputs here on the right. So for every bus route, they could change and restructure the fares based on age. They could also change the time periods and headways or frequencies for any bus route, as well as the type of bus servicing each route. We included 4 different bus types, which varied in passenger capacity, as well as operational costs and emissions. So larger bus types cost more and emitted more per mile than smaller ones. In addition, contestants could choose to provide incentives specific for any vehicle-based mode. So they could be for any trip using transit, using on-demand rides, but actually not for driving, for driving alone, excuse me. And these incentives could be differentiated by age and or income group. So we implemented these incentives so that the agents could not result with cash in hand, meaning that agents would not receive an amount larger than the cost of the trip that they were taking. There were a total of 9 policy objectives by which the contestants had to optimize the inputs. So these included the total vehicle miles traveled, the average vehicle hours of delay per passenger trip, average bus crowding, which was calculated as the average passenger hours spent in a bus filled over its seating capacity. So essentially average passenger hours in a bus where people are standing, signaling discomfort in an overcrowded transit situation. Accessibility, which is visualized on the right, was calculated as the average number of locations of either work or secondary activities that were reachable within 15 minutes from any node in the network. Next, generalized transportation cost is a metric which is the sum of all monetary costs of a trip plus the product of travel time and the value of time. The value of time converts the travel time to units of money. So generalized cost burden was calculated as the average ratio of the generalized transportation cost to household income of a trip maker across all trips in the simulation, and was calculated separately for work and secondary trips. Financial sustainability was a crucial objective, which we included to factor in the public costs of the improvements achieved by a given solution by taking into account the operational cost of public transit and the cost of incentives distributed, balanced out by the total bus revenue. And finally, we included 2 metrics of environmental impact, including the total particulate matter emissions and total greenhouse gas emissions. So the overall score was computed as a sum of 9 score components. Score components were essentially standardized improvement ratios of the value of an objective function for the submission over the value for the BAU. So we first ran a random search, producing about 800 samples to get those standardization parameters for each score component. And since all but three of our objectives were improved using minimization, while accessibility and financial sustainability were meant to be maximized as opposed to minimized, we also included an inversion factor, which we show as alpha I here, to invert those 3 score components such that the scores less than 1 would be optimal across all of the objectives uniformly. The hackathon lasted just over 2 weeks, and we had a great amount of participation with a total of almost 500 registered participants and almost 220 teams. We had about 190 active participants as the competition went on, and 10 finalist teams submitted their valid solutions for a final presentation to a judging panel. Almost all of the teams included some algorithmic component to their solutions, as we expected and had hoped, with the majority of teams using a combination of some a priori knowledge and initial exploration to constrain their input space. And we saw that the top two most popular approaches were Bayesian optimization and evolutionary algorithms, both of which are now implemented and available in the BISTRO optimization library on GitHub. So perhaps unsurprisingly, the majority of the teams treated this problem as a black box optimization problem, and they made hefty use of the computation resources available to them to acquire large samples of the input space in order to get an idea of what might be the optimal solution. A couple of teams actually ultimately found solutions that exploited an unbounded score component, which we had overlooked in the hackathon design. Essentially, since the financial sustainability score component was negative in the BAU, and we chose to invert the improvement ratio for the score, solutions that managed to produce a near zero but positive financial sustainability score produced a very large negative score for that score component. So unfortunately, it was somewhat of a bug and a hack, but it is interesting to note that this loophole in the competition design was actually not discovered analytically by any of the teams. Rather, the optimization algorithm that they had developed eventually found and exploited the issue. So on a positive note, I would say that as a result of the hackathon, we did learn quite a bit about the usefulness of BISTRO, some of the gaps in the way that we had designed it and saw people using it, as well as the relative difficulty in practical interpretation of such a high dimensional input space as the one that we had proposed. So in follow-on research, you'll see that we kind of try to start to go back to square one in terms of the complexity of the optimization problem, and then kind of building out from there. So in this next part of the talk, I'll discuss a study on congestion pricing optimization that we are currently doing using BISTRO. The study, in this study, we wanted to build upon those lessons that we learned from the hackathon and turn our attention to a highly relevant policy, that is congestion pricing, which has really great potential to mitigate for several externalities of the transportation system at once. So we started out with a comparatively simple 4-dimensional set of input variables that defined the location and size of the cordon for congestion pricing. We compared two varieties of this pricing policy. So the first was a simple cordon toll, charging a flat amount per entry in the cordon. And then the second was a mileage fee for all travel within the cordon. So for all car and on-demand ride trips with a passenger, vehicles would be charged, or more so passengers would be charged for all the miles driven within the cordon for that second one, or for the first policy, they'd be charged as they enter into the cordon. So again, this charge applied to either drivers of personal vehicles or passengers of on-demand rides. So another one of our goals with this study was to further our understanding of the trade-offs between objective functions and to investigate the role of weighting in scalarized multi-objective optimization. So you may recall that in the Sioux hackathon that we did with Uber, we chose not to weight the different objectives. And here, what we're doing is actually applying weights to 3 groups of objective functions. So we group them into congestion, social, and toll revenue, and apply a weight to each, to the average of scores within each group. We explored several weighting for scalarization schemes, which are shown on the left here. And on the right, you see raw values of each of the objectives that we included, plotted against the average toll per driving trip. And this is for the Cordon-Based mileage fee. And so that average toll per driving trip is estimated as the product of the road price per mile and the average vehicle miles traveled within the cordon per trip. So as you can see, the objectives are highly correlated within each of the groups we considered. So in the top row, you can see the congestion scores. So that includes VMT, delay, your average delay per passenger trip, and total GHG. And all of these decrease as the average toll increases. which is caused by the impact of that increase in the cost of driving and on-demand rides, which shifts travelers to other modes. Now, the next two, the bottom two on the left, are the average generalized cost burdens for work and secondary trips, and we see that those both increase as the average road price increases, which reflects the higher cost to travel by car, as well as the higher cost burden of switching to walking or transit, as those modes take longer even though they cost less. So finally, we observe in the bottom right of the figure in part F, we observe really a key relationship between the total toll revenue and the average road price, which does appear to be roughly concave. What we see is that the total toll revenue increases as the average road price increases, up into a maximal point where the marginal decrease in driving outpaces the marginal increase in average tolls. So we're encouraged by this, and definitely influenced in which scalarization scheme we chose to put heavier weight on the toll revenue objective. But this was not in pursuit of maximizing profits. Instead, we were just aiming to take advantage of that concavity in the relationship between toll revenue and the input, the average price. So we ultimately chose to optimize the pricing policies using the sixth scalarization scheme shown here. So that included a 40% weight on toll revenue, 40% on the social score, and 20% on the congestion score. The optimization itself was carried out using a Bayesian optimizer called a Tree-Parzen estimator. This approach, which is shown here, estimates two non-parametric probability density functions corresponding to values of the objective that are above or below a threshold. And for this threshold, we chose a value of, I think, 5% of the samples in the history would be better than that threshold. So then new samples are chosen in order to maximize the expected improvement in the objective, given these densities that are estimated from the history of samples. And here on the right, we have a figure showing the progression of the optimization for the Cordon-Based mileage fee in this Sioux scenario, where we see that across the trials, the overall mean and median of the composite scores does decrease as we move along the optimization. Here, we visualize the Pareto fronts of each pair of score components. So hopefully you can see that toll revenue is on the y-axis for the first two figures starting from the left, and then the last figure compares congestion and social, with social on the y and congestion on the x. And what we observe with the results from the Cordon toll on the top and the mileage-based fee on the bottom, that we do see again this convex relationship between, here it's the negative of the toll revenue and the congestion score component. And we also observe a negative relationship between the total toll revenue and the social score component. These relationships are most visible for the mileage fee in the bottom row, although you might notice that the output from the Cordon toll experiment is roughly a subset of the output from the Cordon-based mileage fee. So what we concluded was that the Cordon toll is limited in the extent to which it reduces congestion, although it is also limited to a space of outcomes that are more favorable in terms of cost burden. Here on the left, we have a heat map showing the density of coverage of the Cordons from the top 5% of best performing samples from the optimization. And on the right, you can see the distribution of home, work, and secondary activities in the city of Sioux layered on top of the road network. So we see that the optimal location for the Cordon-based mileage fee is centered slightly southwest of the Central Business District in Sioux, and it covers areas where both work and secondary trips are located, but there's less density in places where most of the home locations are located. So this is the last of the results that I'll share for now, as we are still working through this this research, but this is quite exciting. We were able to approximate a three-dimensional representation of a theoretical concept from economics, which is called the Laffer curve. And the Laffer curve is typically discussed in the context of taxation, as it plots the concave relationship between total tax revenue and a tax rate. And in our context, the tax rate is variable per person, and it depends on the portion of their trip that lies within the cordon and the mileage rate of a given policy. So here we show the total toll revenue with respect to both the road price and the average tolled miles per trip. So it's the average number of miles that are actually within the cordon for each passenger, or for each trip that is that can be tolled. So we see that there appears to be a global maximum with respect to these two design variables. And we also observe that there seems to be a concave relationship between the toll revenue and average tolled BMT per trip for fixed road prices. So as you move left or right for any fixed road price, you can see that relationship. So again, let's see, I'll note that we did not seek to maximize toll revenue for the sake of maximizing profit, but rather we were trying to take advantage of this existence of a maximum in that relationship to drive the optimization to completion. Because as you saw, if the balance tips to either the congestion or the social scores of the optimization, will just push to one side or the other in terms of either try to maximize tolls and cover the whole city so that no one drives and we reduce congestion, which isn't really a feasible or desirable result, or it goes to the other side where it just reduces tolls in order to minimize the social cost. So I will note that this study was performed on a benchmark scenario, and it certainly has a number of limitations. We're certainly not ready to say that these results are directly applicable to the road pricing that should be implemented in a city such as Sioux Falls. Note Sioux, please. But the results do demonstrate that the potential of agent-based simulation with these activity-based travel models, as we use in BISTRO, can have great potential to predict and analyze behavioral responses to real policy interventions, and they're even lining up with some of the established theory in economics. So as we wrap up, this initial research that we're doing on congestion pricing in Sioux is also being augmented by an effort to build out a scenario that represents the city and county of San Francisco using existing model from Bayen called the SF Light model. And we are hoping to produce more valuable, actionable insights regarding the placement and structure of congestion pricing in a city such as San Francisco, and also include optimization of complementary policies such as subsidies and transit service adjustments, as we had demonstrated that we could do with the Sioux hackathon that we had done previously. And in addition, we are investigating a Pareto-based objective function that maintains the multidimensionality in the optimization in comparison to the aggregated scoring functions that we have explored to date. And finally, and potentially one of the more exciting efforts is the prospect of developing a transfer learning approach to make use of data across scenarios, or even within a scenario across sample sizes, in order to leverage those insights across experiments or variations in the same experiment, and potentially develop optimal policies that can withstand changes or disruptions in the business as usual and maintain their optimality. So I'd like to thank my advisor, Professor Alex Bayen, and all of these colleagues shown here that have contributed to BISTRO. from the initial development through to ongoing development of the software and execution of the research that I've presented today. All of these folks have been instrumental in this work. And finally, you can find out more about BISTRO and the research I've presented at our website, bistro.its.berkeley.edu. And you can also use and contribute to the platform at our GitHub, linked here. Thank you so much for your attention, and I'm looking forward to your questions and comments later in the workshop. Take care and have a good rest of your morning. Bye-bye.